Assalamualaikum. This is your Thermodynamics 2 class. So at this time there's only 4 students. So where are the rest of the students? So can anyone text the rest of the students to kindly join the lecture? Okay, so we can start now. Okay, so today is your lecture number 13. So can anyone confirm that what's up your on screen right now?
Sir, lecture 13, chapter 9, gas power cycle.
Okay, thank you. Okay, so again, this is your gas power cycle lecture, which is related to your diesel cycle. But in this lecture, we will discuss another type of diesel cycle. So, in previously, we discussed about diesel cycle where there will be a constant pressure heat addition process is involved. But there will be something which is associated with this process because it will turns out to be an incomplete burning of the fuel in your diesel cycle. Okay, so this can be one flaw for related to diesel cycle. So in order to overcome this flaw, that in order to overcome the incomplete burning of fuel during the combustion process, what we have to do is we have to just divide the process of constant pressure heat addition into two different processes. That is constant volume heat addition and constant pressure heat addition. Okay, and the cycle then it is called the dual cycle because there will be two processes involved in the combustion process. Okay, but still it is a type of dual cycle. So we will today discuss about the dual cycle. So if you can just look the schematic diagrams for the dual cycle, you will clearly understand about it. Okay, so in the actual cycle, if I just talk about the actual one, so there will be intake stroke as we discussed in the previous lecture as well, then there will be compression stroke, then there will be power stroke, and then exhaust stroke will take place. But when we are talking about the dual cycle, what we have to do is in comparison to diesel cycle, we just have to divide the process of the heat addition, which is in case of diesel cycle constant pressure, into two processes. One is constant volume heat addition, and then it will be a constant pressure heat addition process. And the advantage of this doing this is to make the complete combustion of the fuel. Okay, because if there is an incomplete combustion of fuel, then it may cause excessive vibration in your engine. Okay, so that will also the result in the incomplete burning of the fuel. So in this case, when we implement these two type of heat addition process, we can reduce that vibrations as well, and then definitely the efficiency will also increase because if we are burning the fuel and we are getting more energy out of the fuel in turn of the complete burning, so it will result in the more efficient cycle as well. Okay, so the rest of the processes are same. Compression process is there, expansion process is there, constant volume heat rejection process is also there. Okay, so now we will see that what are some different advantages and where we have to use the dual cycle in our daily life. Okay, so it is an internal combustion four-stroke engine, and then dual because combustion take place in two parts. First at constant pressure and second at constant volume. Okay, so that's why it is called dual cycle. This makes it better than diesel engine cycle. So definitely, if there will be a complete burning of fuel, it makes this type of cycle better than the diesel engine cycle. And it is also known as limited pressure or mixed cycle. Okay, so mixed cycle because it is a mixture of Otto cycle, because if you can remember that in Otto cycle it is constant volume heat addition process. Okay, so in this case of dual cycle, both constant volume heat addition is involved and both constant and also the constant pressure heat addition is involved. So it's mean that Otto cycle and diesel cycle both are involved in it. So that's why we call it as a mixed cycle. And the thermal cycle, that is a combination of Otto and the diesel cycle. Dual combustion engine are most commonly used for mobile propulsions in vehicle and portable machinery. Okay, so now the important point is that where we have to use this dual cycle in our daily life. So most commonly it is used in the ship industry. Okay, so where we have to need where we need more torque and also we need to get more energy out of our fuel. Okay, because there will be a limited fuel in your ships, so that's why we need this type of engines in our ship industry, and then it is also used in our helicopter system as well. Okay, and most importantly, if you can see in our daily life for today, diesel engine automobiles, and most of these automobiles are working on basically on a dual combustion engines. Okay, either it is mentioned over there it is a diesel engine, but nowadays mostly it is a dual combustion engines, today's automobiles as well. Okay, so coming towards the processes which are involved in the dual cycle. So again, the first process is the isentropic or adiabatic compression process, which is similar to the diesel cycle and Otto cycle as well. Then there will be a constant volume heat addition process. Okay, so it's mean that there will be it was related to Otto cycle, and then it will be a constant pressure heat addition process, which we see in the diesel cycle, and then isentropic expansion, and then there will be constant volume heat rejection, which is similar to Otto and diesel cycle. Okay, so we will try to draw the PV diagram and TS diagram so that you will get better understanding of it, what's happening in the dual cycle. Okay, so starting from the PV diagram first. Okay, so as you know, for the isentropic compression, if there will be a point 1 over there, okay, so after compression process, it means that your volume will decrease. Okay, so point number 2 will be, you can say it will be over there or something. Okay, so you can say it will be point number 2. Okay, from 2 to x. Now I have just denoted over there will be a point x. Okay, so where there will be end of constant volume heat addition, and also there will be a start of constant pressure heat addition. Okay, so from 2 to x it is a constant volume heat addition, so it's mean that the volume until point number x, so you can say it will be x point, the volume will be constant. Okay, so it will be the straight line. Okay, so 2 to x is constant volume, then there will be x to 3 is constant pressure heat addition. So x is the starting point of your constant pressure heat addition, and it ends at point number 3. Okay, so this is your constant pressure heat addition. Then there will be isentropic expansion. So as you already know that for expansion process, the volume will increase after your expansion process. So if point number 3 is here, so your point number 4 will be somewhere there. Okay, so this is the point number 4, and then from 4 to 1 it is constant volume heat rejection process. Okay, so it means 4 to 1 volume is constant. So I just write this one, and this is your 4 to 1 constant volume heat rejection process. Okay, so now if I just denote over there, this is your compression process, this is expansion process, isentropic one, this is QR, and now here there will be two Q addition. So this is Q in and this is also Q in. Okay, so now if we want to find total Q in, we have to add these two Q in, which is one is at constant volume and other one is at constant pressure. Okay, so this is the PV diagram. So now we will try to draw the TS diagram as well. Okay, so from 1 to 2 it is a isentropic compression process. So it's mean that if I can say to point number 1, so point number 2 it will be here, and it is an isentropic process, so you can just draw one line and join point number 2. Okay, so now from 2 to x it is a constant volume heat addition. So as it is a heat addition process, so it's mean whatever the temperature at point number 2, the point number 3 will be above than point number 2 temperature. So you can say the point number 3 lies above than point number 2, and you can just join. Okay, so this is your Q in, and you can also say it will be the constant volume. V is equal to constant. Okay, so now from constant pressure heat addition, so as okay, so you can say it will be x. Okay, sorry, because I have denoted with the x, so you can just say it will be x point. Okay, so from x to 3 it is a constant pressure heat addition. So whatever the temperature at point number x, your point number 3 will be above than point number x. So it's mean that I can say this point number 3 will be somewhere there. Okay, so you can just, and you can say it will be the constant pressure, and this is also Q added. Okay, so now from 3 to 4 it is isentropic expansion process. So it's mean that entropy is constant, and your whatever the temperature at point number 4, the temperature at point 1 will be less than point number 4 because it is a constant volume heat rejection process. So I can just draw one line and okay, so this is the Q out. Okay, so this is the TS diagram associated with your dual cycle. So I hope there will be no confusion over there. If you have any question, you can also ask me.
Excuse me, sir.
G.
सर ये पॉइंट एक्सरसाइज बोला था आदित्य जो 28 ज्वाइन किया.
Okay, so point X is any point, you can abbreviate with anything. For example, I can say it will be A, B. Okay, so in the dual cycle, what we have to do is there will be two processes involved in it. So one is the constant volume, one is the constant pressure heat addition process. So X point, you can say it will be point number, for example, if you have confusion with the X, you can say it will be 3, then there will be 4, 5, okay, so you can denote it with any point, okay, so that you can just make a symmetry over there. So for X point, you can say it will be the end of constant volume heat addition process and start of constant pressure heat addition process in the dual cycle. Okay, so this point is X, so you can denote it with any number, either you can say it will be 6, 7, 8. Okay, so it's depend on you.
Okay, sir.
Okay, so as we have to analyze this type of dual cycle also thermodynamically, so in order to do that, we have to develop some sort of equations, which is the efficiency equation, the energy in the Q in equation, which is the added heat, and also the Q rejected. So now we will look for it at how to build the efficiency equation in terms for the dual cycle as well. Okay, so starting from again PV and TS diagram, so there here there will be a clear representation of these diagrams so that you will clearly understand, and that's I am talking about, so do not confuse over there. In the previous thing I have just denoted with X, so here it is denoted with 3, okay, so that you will not get any confusion over there. So 2, 3, 4, 5 and 1, okay, so that will make a symmetry over there. So again in the TS diagram also 1, 2, 3, 4 and 5. Okay, so starting from the again, we already know whenever we have to develop the efficiency equation, we have to start with the energy balance equation throughout our cycle. Okay, so if we can say the Q added, so we can say Q total. So Q total add is the combination of the heat added between these 2 points. So Q23 and Q34. Okay, one is constant volume. So for constant volume, we already know it will be 2, 3. So there will be one heat addition between 2, 3, and there will be another heat addition between 3, 4. Okay, so for constant volume heat addition process, we know the equation CV temperature T3 minus T2, which is similar to your Otto cycle. Okay, and Q in for constant pressure, we already know it will be represented by Cp and T4 minus T3. Okay, so which is related to your diesel cycle, which we already discussed in the diesel cycle as well. So here we have to add both of these terms, so in order to get the total heat addition process. Okay, so now coming towards the Q out. Okay, so Q out is constant volume heat rejection process, so it's mean that it will be Cv T5 minus T1. Okay, so now we have the both equation, which is Q in and Q out. So from there we can develop one equation for efficiency. Efficiency of dual is 1 minus Q out over Q in. Okay, so in I have just put, okay, so you can just say it will be equation number A or equation number B, or you can just put in the equation number C. Cv T3 minus T2. So I'm just putting the values from A and B to C. Okay, so from here, if I can just take common from the numerator Cv and from the denominator also Cv, so it turns out to be 1 minus T5 minus T1, T3 minus T2, Cp over Cv becomes K, because if I take the common, it will be in the denominator, and then T4 minus T3. Okay, so now this is the equation for the dual cycle, and you can write it as equation number 1. Okay, so this is the equation in terms of temperature. Okay, if we have the temperature's value, we can easily find the efficiency of dual cycle by using this type of relation. But here what we have to do is we have to make one equation which is the function of compression ratio and cutoff ratio, as we already developed in the diesel cycle case as well. So in this case also we will try to develop similar type of equation. So you have to note down the equation first and keep it, remember this equation number 1, because we have to use it for the next part as well. Okay, so you have to note it down, then I move towards the next part. Okay, so in order to develop the equation which is the function of compression ratio, cutoff ratio, in the previous case also we have developed, we have to find the values of temperature at all the point in terms of compression ratio and in terms of cutoff ratio, so that we can put in the equation number 1 to get the efficiency equation as well. Okay, so starting from process 1 to 2. Okay, so as you know, it is the isentropic process, so the relation that is valid is T2 over T1 is equal to V1 over V2 K minus 1. Okay, specific heat ratio minus 1. And if you already know that your compression ratio is V1 over V2, which is the maximum volume over minimum volume, so you can say it will be Rk minus 1, and you can denote with equation number 2. Okay, so now from point number 2 to 3, so we already know it will be a constant volume heat rejection process. So we can say it will be P2 V2 over T2 is equal to P3 V3 over T3. And as it is a constant volume process, so I will just eliminate the volume, and it's turned out to be T3 over T2 is equal to P3 over P2. Okay, so from here we have to add another term, okay, in comparison to the diesel and Otto cycle. So this P3 over P2 is called beta, P3 over P2, and this beta is called the pressure ratio, okay, and also it is called the explosion ratio. Okay, so it will be related to the process which is constant volume heat addition process. Okay, so any temperature pressure ratio between point number 3 and 2, we can say it will be the pressure ratio. Okay, and we can also write T3 over T2 is equal to beta, or also we can say T2 is equal to T3 over beta, and you can mark it as equation number 3. Okay, so this all we are doing because we have to find all the temperature value in terms of compression ratio or in terms of cutoff ratio, and also in terms of beta here. Now there will be a pressure ratio also involved, so that we get one efficiency equation that is a function of all these three variables. Okay, so now coming towards the process which is between 4 to 5. So as 4 to 5 is also isentropic process, so we can say T4 over T5 is equal to V5 over V4 K minus 1. Okay, so from here we can also write that V5 over V4 is equal to, because if you can just remember that V5 is equal to V1. Okay, so we can say V1 over V4, and if we can just multiply and divide V2, okay, so it will not make any difference in comparison to the V1 or V4. Okay, so it is the same thing. Okay, so from here I can just write that V2 is equal to V3, okay, because the volume at point number 2 is equal to volume at point number 3. So V1 over V2, V3 over V4. And here, if you can remember, it is V1 over V2 is the compression ratio, and V3 over V4 is the cutoff ratio, okay, which we already discussed in the diesel cycle case as well. Okay, and from there we can easily write that V5 over V4 is equal to R over RC. Okay, so V5 over V4 is equal to R over RC, and if we can just put this V5 over V4 value into this equation, so it turns out to be R over RC K minus 1. Okay, so this equation you can mark it as equation number 4. Okay, so you can write it down. If you have any question, you can ask me. Then we'll move towards the next part.
और आरसी का चीज कहाँ से आई? इसके वे छोटी सी डेरिवेशन की बता सकते हैं
जी
आर और आरसी किस तरह बन गया V5 और V4?
अच्छा ओके अगर आप इसको सॉल्व करेंगे V1 और V2 डिवाइड बाय V4 और V3 बट इट्स टर्न आउट टू बी V1 और V2 इंटू V4 और V3 और अगर आपको रिमेंबर हो तो V1 मैक्सिमम वॉल्यूम V2 मिनिमम वॉल्यूम इट इज द कंप्रेशन रेशियो सो दिस इज द R V4 और V3 इज द कट ऑफ रेशियो ओके सो इट इज RC
ठीक है सर
ओके
यस सर
ओके Okay, so now between point number 3 and 4, it is a constant pressure heat addition process. So we can also write one equation between this process as well. So P3 V3 over T3 is equal to P4 V4 over T4. Okay, so as it is a constant pressure process, so pressure will be eliminated from this side and T4 is equal to T3 V4 over V3 and also it will be RC because V4 over V3 is the cutoff ratio and it into T3. Okay, so now what we have to do is we have to put the value of T4 which we already derived from this one into equation number 4. Okay, so if you have to refer back to your previous slide, so equation 4 is T4 over T5 V5 is equal to V5 over V4 K minus 1 okay and is equal to R over RC K minus 1 which we already developed in the previous slide. Okay, so in that equation we have to put the value of T4 and it turns out to be RC T3 T5 R over RC K minus 1. Okay, so from here we can easily find the value of T5. Okay, so if I can write over there T5 is equal to RC T3 RC over R K minus 1. So I've just rearranged this equation. Okay, and it turns out to be T5. Okay, so now what we have to do is put the value of T2. Okay, so the value of T2 comes from equation number 3. Okay, so if you can just go to your previous slide or you can just refer back to the equation number 3. So you have to put the value from equation 3 to equation number 2. Okay, and that turns out to be T3 over beta over T1 is equal to Rk minus 1. And from here I can say it will be T1 is equal to T3 over beta pressure ratio 1 over R K minus 1. Okay, so now all the values are in terms of T3, in terms of compression ratio, in terms of pressure ratio, or in terms of cutoff ratio. Okay, so T3 can easily be eliminated if I put all these value into equation number 1. Okay, so now you have to refer back to your equation number 1. So equation number 1 is which is the efficiency of dual cycle equation, 1 minus T5 minus T1. Okay, if I can just write over there, T5 minus T1 over T3 minus T2 KT4 minus T3. Okay, so I have to put all the temperature values which I have already derived. Okay, so either it will be T5, T1, T4. Okay, so T2. Okay, into equation number 1. Okay, so that we can get one equation which is a function of your compression ratio, which is a function of pressure ratio, and also it will be a function of cutoff ratio. Okay, so you have to note it down, then I'll move towards the next part. Okay, so now your equation 1 become 1 minus, so if I can just put the value of T5, so it will be RC T3 RC over R K minus 1 minus, and if I put the value of T1 into equation number 1, it will be T3 by beta dot 1 over R K minus 1, and in the denominator it will be T3 minus, if I can put the value of T2, which is T3 over beta plus specific heat ratio RC T3, which is the value of T4 minus T3. Okay, so now if you can just see that it will be the function of T3, so I can easily eliminate T3 if I can take common from the numerator, and if I can take the common from denominator as well. Okay, so I can just write 1 minus 1 over R K minus 1 R C K 1 over beta. So I will just rearrange this equation number. You can say it is equation number 6 or 7, you can whatever you want to write. 1 minus 1 over beta Okay, so this is the equation, which is now you can easily see that it is a function of compression ratio, it is a function of pressure ratio, and it is a function of cutoff ratio. Okay, so I can just rearrange it again, and it will be 1 over R K minus 1 dot pressure ratio RC cutoff ratio to power K minus 1 pressure ratio minus 1 plus K into pressure ratio into cutoff ratio minus 1. Okay, this is the same equation. I will just rearrange equation number 7, and it turns out to be equation number 8. Okay, so now this is the equation for your dual cycle, and this equation is not available in your books, it is from your reference book, so that's why you have to listen it to carefully that how to develop this type of equation, because the proof is not available in your book as well. Okay, and if you can just look into this equation, which is the dual cycle, and if you put the value of RC is equal to 1 in the equation number 8, it turns out to be the Otto cycle efficiency equation, which is 1 minus 1 over R K minus 1. And similarly, if you can put beta is equal to 1 in the equation number 8, it's turned out to be the diesel cycle efficiency equation. Okay, so if you can just put the beta is equal to 1, it is the same equation which we developed in the diesel cycle efficiency. Okay, so this is the proof for the dual cycle efficiency. If you have any question, you can ask me, or then we can move forward towards the next slide. You can just note it down. Okay, so this is the equation which we already developed in the previous slide. Is mentioned over there. Set your efficiency for the dual cycle. So if it is written diesel, so do not confuse over that point, because the dual cycle is also the type of diesel cycle. Okay, so somewhere if it is written that diesel dual cycle, so you can just remember that this is the equation 1 minus 1 over r k minus 1. So here in this equation it is denoted by alpha, the pressure ratio, and we have denoted with beta. Okay, so here there will be alpha, and rest of the equation is same. Okay, and this equation is valid for constant specific heat problem. Okay, so if there will be assumption that you have to find the cold air standard efficiency, so if and if you have the value of compression ratio, cutoff ratio, and pressure ratio, you can just put the values in this equation and you can easily find the efficiency for cold air standard assumption. Okay, so now here it is the equation for variable specific heat problem. So for that you have to find the value of internal energy from 4 to 1, which is constant volume heat rejection process, and also you have to find the internal energy for constant volume heat addition process, which is ux minus u2, and then you have to find the enthalpy value for constant pressure heat addition process. Okay, and for this you have to find the values from thermodynamic table. Okay, and this is the similar thing which I am talking about. If you have to put RC value is equal to 1 in this equation, it turns out to be this, and if you can put value of beta, which is pressure ratio, into this equation, it turns out to be efficiency of your dual cycle. Okay, so now if you have to remember that if in the question it is mentioned that explosion ratio or pressure ratio, it means that beta value is given in your question or in the problem. Okay, so now I think we will take the break for 20 minutes for prayers, and then we will join again at 1:30. Okay, so if you have any question, you can ask me, and then we will go for the break. Okay, so starting again from the problem. Okay, so we will discuss one problem related to dual cycle so that you will get the better understanding how to solve the problem in which dual cycle is involved. Okay, so first you have to read the statement. Okay, so the compression ratio of an ideal dual cycle is 14. Okay, so that's mean R is given. Air is at 100 kilopascal and 300 Kelvin at the beginning of the compression process. So pressure 1 and temperature 1 is mentioned in your question. The beginning of compression process and at 2200 Kelvin at the end of the heat addition process. So it's mean that the point number you can say it will be point number 3, okay, in your TS diagram or in your PV diagram if you just correlate with your PV diagram from your previous slide. Okay, so the pressure increased by a factor of 1.58 during constant volume heat addition process. Okay, so the pressure increased by a factor, so it's mean that the ratio P3 over P2 is equal to 1.58. Okay, so this is given in your question. Okay, so if you can just make it more elaborated, it will be 1.58 P2, where it is mentioned that pressure increase, that because P3 there will be an increase in pressure and it will be increased by a factor of 1.58 into P2. Okay, so heat transfer to air take place partially at constant volume and partially at constant pressure, and its amount is 1520. So it's mean that your total Q is mentioned in your question, which is a combination of two processes, which is constant volume heat addition and constant pressure heat addition. Assuming the variable specific heat, so it is a variable specific heat problem, so we have to find out all the internal energy values and also enthalpy value for different points. So first thing is we have to find the fraction of heat transfer at constant volume, and then we have to find thermal efficiency of the cycle. So this is the question, so you have to note down the data first and then I will move towards the solution of this question. Okay, starting from the PV diagram. Okay, so this type of PV diagram is also mentioned in your book, so that's why I just make this point as an NX over there. Okay, so I hope there will be no confusion how to draw this type of PV diagram for dual cycle. Okay, so starting from the data which is available in your question, so it is mentioned that the temperature 1 is 300 Kelvin. Okay, so we have to find the values associated with U1, we have to find U4, we have to find U2, we have to find UX, also we have to find from the data, and then enthalpy at point number 3 and enthalpy at point number x we have to find. Okay, so these all the variables we have to look for the in the thermodynamics table. Okay, so for the point number 1 we can just go to table A17, so I am not going towards the table A17, you have to do it by yourself. I will just mark the value over there. So the value is U1, that is associated with this 300 Kelvin, is 214.07 kilojoule per kg from table A17. Okay, as you already know, whenever we have to practice the variable specific heat problem, we have to find other variables also, so that it will be easy for us to find the different state properties. So here we also have to note down the relative specific volume at point number 1 from the same table. So it will be 621.2, which is a dimensionless quantity. Okay, so now we have to find other parameter, because at point number 2 we do not have the temperature value, so and we do not have the any data which is available for point number 2, so that's why we have to find relative specific volume at 2 in order to find the value of U2. Okay, so we already know that for isotopic process, relative specific volume at 2 over relative specific volume at 1 is equal to V2 over V1. Okay, and from here you can also say that 1 over R relative specific volume 1, okay, which is equal to VR2. Okay, so if in this question you can put in this relation you can put the value of R, which is mentioned in your question 14, and relative specific volume at 1 we have just find from the previous state, so 621.2, and if you can just solve it you will get the value 44.37, also the dimensionless. Okay, so now VR2 value is known to us, so now we just look the value of internal energy according to this value, which is VR2 value, and by using the first interpolation you will get the value of U2, which is equal to 611.2 kilojoule per kg. And again you have to find another parameter also, because we need the value of x as well, ux as well. Okay, so for this we can just take the value of T2. So T2 value, again by using the interpolation you can easily find by using table A17. So 823.1 kilojoule per kg. Okay, so now coming towards the process number 3, because for the process number 3, which is point number 3, the temperature is given that at the end of heat addition, constant pressure heat addition process, the temperature is 2200 Kelvin. So T3 is 2200 Kelvin, which is mentioned in your question. So against this value from the same table, because it is a constant pressure process, so that's why you need the value of enthalpy. Okay, so H3 is equal to 2503.2 kilojoule per kg, and also we can take one another variable, relative specific volume at 3, 2.012. Okay, so now we can say that Q in, which is the Q total. Okay, so you can say Q total in is equal to Q x2 plus Q 3x. Okay, and from this you can say ux minus u2 plus h3 minus h2, h3 minus hx, sorry. Okay, so in this question, in this relation, h3 value we have just find, u2 value is known to us, ux and hx value is not known to us right now. Okay, so we have to find this value. Okay, so how to find this value? So if you have just remembered from the problem statement, that in the problem it is given that the pressure ratio, that is P3 over P2 or Px over P2 is given in your question, which is 1.58. Okay, so what you have to do is you have to apply one relation, P2 V2 over T2 is equal to Px Vx over Tx. So I'll just add one equation, relation for this point number x and 2. Okay, so from here I can say that because it is a constant volume process, so volume will automatically eliminate it, and from here I can say Tx is equal to T2 Px over P2, and this Px over P2 is available from your problem statement, which is 1.58, and T2 value we have find out here. So if I can say that T2 value is 823.1 and P2 value is 1.58, and if I can solve it, it will be 1300 Kelvin. Okay, so T2 temperature is given to us now, 1300 Kelvin, by using this type of relation. Okay, so you can note it down, then I'll move towards the next part. So if you have any question, you can also ask me. Okay, so now we have the value of Tx is equal to 1300 Kelvin. So you have just go directly to thermodynamic table. You can easily find the temperature range for 1300 Kelvin, and you have to note down the value of enthalpy Hx is equal to 1395.97 kilojoule per kg, and Ux value is equal to 1022.82 kilojoule per kg. Okay, so this value we can easily find in the thermodynamic table. Okay, so this all because we are doing, because we are interested in to find the value of Ux, because the first part is to find the fraction of heat that is added between the constant volume heat addition process. Okay, so for that we have to find the Qx2 or Q2x. You can just 2 minus 2x Ux minus U2. Okay, so Ux value is known to us, so 1022.82, and U2 value we have already found in the previous step, which is 611.2 using the thermodynamic table, and you can just solve it and you will get 411.62 kilojoule per kg. Okay, so this is the Q, which is heat added for the constant volume process. Okay, so now if we have to find the fraction of heat, so for fraction of heat you can denote with Fh. Okay, so that will be the ratio for the heat that is added for Q2x and Q total. Okay, because if you can just take the ratio of these two, you can easily find the fraction or amount of heat that is added during this process. Okay, so 411.62 or 1520, which is mentioned in your question, that it is the total heat. And from here, if you can just take the ratio and you can just convert it into the percentage, you will get 27.1% is the fraction of heat that is added during constant volume heat addition process in the dual cycle. Okay, so this is the solution for your part number A. So you can note it down, then I'll move towards the part number B. Okay, so in the part number B, we have to find the efficiency. Okay, so for efficiency, you already know that 1 minus Q out over Q in. Okay, so Qn is known to us from the problem statement. Q out we have to find first. Okay, so Q out is equal to U4 minus U1, because it is a constant volume heat rejection process, so that's why we are uh, interested in the internal energies. Okay, so U4 value is not known to us. U1 value we have find in the part A. Okay, so first step is to find the U4 value. Okay, so for U4 value we need any variable at point number 4, so that we can easily go to thermodynamic tables. Okay, so for that we can say VR4 over VR3, because it is an isentropic process, so we can say V4 over V3. Okay, but the here problem is that we do not have the value of cutoff ratio as well, so that we cannot find this V3 easily. Okay, so first also we have to find the value of V3. Okay, so for V3 we can develop one relation, which is, okay, so you can just note over there P3 V3 over T3 is equal to Px Vx over Tx, as it is a constant pressure process, so that will be eliminated, and here you can say that V3 over Vx is equal to T3 over Tx, and V3 over Vx is your cutoff ratio. Okay, so for cutoff ratio it is the value is mentioned in your because cutoff ratio we have the value in the problem or not. Okay, so cutoff ratio we do not have the value, so V3 over Vx is equal to 2200 Kelvin over 1300 Kelvin. Okay, so from here we will just solve it, and V3 or Vx is equal to 1.692, which is Rc. So now we have the cutoff ratio value. Okay, so from this value we can easily find the value of V3, because V3 is equal to 1.692 into Vx. Okay, by using the cutoff ratio. So I can just put over there that V4 over 1.692, or I can also say it will be V2. Okay, because Vx and V2 is equal, both are same. Okay, and from this one I can say also that it will be equal to R over 1.692. Okay, and from this VR4 turns out to be, because VR3 is known to us. Okay, so you can just multiply 2.012, which is VR3 value, into the compression ratio is 14 and 1.692, and from here you can easily find the relative specific volume, which is 16.648. Okay, and by using this value, which you can take as a reference point and go to thermodynamic table, and you can easily find the value of U4 by using the interpolation. Okay, so 886.3 kilojoule per kg is the value of U4 from table A17. Okay, so now U4 value is known to us, so we can easily find the value of Q out. So if I can just put the Q out value or U4 value in the Q out equation, it will be 886.3, and minus U1 value is 214.07, and I can solve it, and it will be 672.23 kilojoule per kg. Okay, so now Q out is known to us, so I can put the value in this one. So 1 minus 672.23, 1520 is the total Q in, and if I can solve it, it will be 55.8% of your thermal efficiency for dual cycle. Okay, so this is the part number B. Okay, so the solution is done. If you have any question, you can ask me.
तो जो X3 वाला प्रोसेस था इसका नाम क्या था?
Constant pressure heat addition process.
Okay, sir.
So you can note it down, then I will move towards the next question, okay, which is also related to dual cycle. Okay, so now this is another question which is also related to dual cycle. Okay, so first you have to read the statement. So a swept volume of diesel engine working on dual cycle is 0.0053. So I hope you have all remembered that what is the swept volume. So swept volume is basically the volume inside your cylinder when you're between the points of TDC and BDC. Okay, so it is in between TDC and BDC, but the volume is occupied is the swept volume. And the clearance volume is 0.0035. So clearance volume, I think you all know that it will be the minimum volume. So the minimum volume is 0.00035 meter cube. The maximum pressure is 65 bar. Okay, so now here another important term which is added is the fuel injection ends at 5% of the stroke. Okay, so this we will look then when we are going to solve the problem, that how to insert the data and how to find other parameters. The temperature and the pressure at the start of compression are 80 degrees Celsius and 0.9 bar. So T1 and T1 is given. Determine the cold air standard efficiency of the cycle. So it's mean that it is related to constant specific heat value problem. Okay, so you can implement directly the relation which we already developed in the previous slides as well, which is the efficiency of dual cycle in terms of compression ratio, in terms of pressure ratio, in terms of compression ratio, in terms of cutoff ratio. Okay, so now you have to just note down the data first, and then I'll move towards the solution of this type of question. Okay, so again you have to just draw the first PV diagram for the dual cycle, and then we will look for it that what data is available. So in your question it is mentioned that the swept volume is, so if you can say that it will be TDC and this is your BDC. So the swept volume is the volume, this is your swept volume. Okay, so now the clearance volume is the volume until this point number 2, from 0 to point number 2. Okay, so now in the question it is mentioned that, okay, so if we can note down that V1 over, because compression ratio is not given, so V1 over V2 is the compression ratio, and we already know that the value of V1 is equal to the swept volume, which is Vs plus Vc, which is the clearance volume, and if we can add, it will be your volume at point number 1. Okay, so we can just say that swept volume plus V clearance volume, which is at point number 2, and V2 is also a clearance volume. So V2, if we can say, it will be Vc. Okay, so now all the values are given to us in the question. So swept volume is 0.0053 meter cube. Clearance volume is also given in the question, which is 0.00035, or if you can just divide with the clearance volume 0.00035, you can easily find the value of R. Okay, so R value is turns out to be 16.14. Okay, so this is the compression ratio, because we have to find all the values of compression ratio, cutoff ratio and pressure ratio, so that we can easily insert all the values into the efficiency equation. Okay, so now here the cutoff ratio is also not mentioned. So as you already know that cutoff ratio is equal to V4 over V5. So cutoff point, and this is your point number 5. Okay, so in your problem statement it is mentioned that the maximum the fuel injection end at 5% of the stroke. Okay, so what does this mean? It's mean that your V4 point is equal to 0.05, which is 5% of the stroke. Okay, so for the stroke I can say it will be V swept. Okay, because if you remember that the stroke is also the distance between TDC to BDC. Okay, and whatever the volume which is in between your stroke is the swept volume. Okay, so that's why I just write over there Vs. And then if we can say that V4 is equal to 0.05 Vs plus V3. Okay, sorry, it is V3 point. Okay, so do not confuse over there. It is the point number V3. Okay, so now this is the equation, and now we have all the value of Vs also, V3, because V3 is the clearance volume. Okay, so now we can put the values in it, and we can easily find the cutoff ratio. So it will be 0.0053. Clearance volume is 0.00035, 0.00035, and from here if you can I can solve it, it will be 1.76, which is your cutoff ratio. Okay, so now RC is known to us. Now the remaining variable which is which we have to put in the efficiency equation is the pressure ratio or beta. Okay, so in order to find the beta, we already know beta is equal to P3 over P2. Okay, so in your question it is mentioned that the maximum pressure is how much? 65 bar. So maximum pressure is at point number 4 and 3 because P4 is equal to P3. Okay, so it will be 65 bar. But P2 is not known to us. Okay, so first we have to find out P2. Okay, so if you all remember that for the isentropic process, we already know that P2 or P1 is equal to V1 over V2 specific heat ratio. Okay, so from here I can easily find the P2 value because P1 is known in your question because P1 value is 0.9 bar. Okay, so from here 0.9 bar and V1 over V2 is your compression ratio, which we already find in the previous step 16.14, and value of K is 1.4. And from here I can just put all the values and solve it. 44.22 bar is your P2 value. Okay, and from here I can easily find the pressure ratio also 65 divided by 44.22, and from here I can get 1.47. Okay, so this is the beta. Now we have all the three variables beta, RC and R, and if I have these three variables there will be no difficulty to find the thermal efficiency for the constant specific heat problem. So you have to note it down, then we'll move towards the next part. If you have any question you can also ask me.
एक्सक्यूज मी सर, ये थर्ड स्टेप जरा दोबारा कर दीजिएगा। यहाँ पे V4 की जगह 0.05 VS की है, ये कैसे है?
0.05 किस तरह है? अच्छा मैं आपको बताता हूँ। Okay, so in your question it is mentioned that the fuel injection end at 5% of the stroke. Okay, so fuel injection is ending at point number 4. Okay, so this is the main point, that where your fuel is fuel injection is ended. So it is point number 4, and it is mentioned it is 5% of the stroke. Okay, so if you already know that this is your stroke, okay, total length, which is from BDC to DDC. Okay, and it say that your point number 4 is 5% of the stroke length. Okay, so it's mean that it is 5 over 100 into whatever your stroke will be. So it will be 500 5 divided by 100 into stroke. Okay, so it turns out to be that this point from 3 to 4 is 0.05. We can say it will be swept volume. Okay, because swept volume is the volume which is occupied during your stroke. Okay.
Okay sir.
Okay, and if I can say that what is the volume at V4, so V4 is the volume that is 0.05 Vs plus V3, which is the clearance volume. So it turns out to be like this.
Okay sir.
Okay, so now coming towards the dual cycle efficiency equation, so which we already know that it will be 1 minus 1 over R K minus 1 pressure ratio RC K minus 1 beta minus 1 pressure ratio minus 1 plus beta into specific heat ratio cutoff ratio minus 1. Okay, so this equation we have already developed, so just you have to put all the values in this equation and you can easily find. So R value is 16.14 and this is 1.4 minus 1. Beta value we have find 1.47, so 1.47. RC value is 1.76 to power 1.4 minus 1. Beta value is 1.47 minus 1 plus 1.47 into 1.4 is the specific heat ratio, and RC value is 1.76 minus 1. Okay, and from here you can just solve it and you will get the value as 0.6383, and if I can just convert it into the percentage, it will be 63.83% of your efficiency for dual cycle, and this is for cold air assumption. Okay, so this is the solution of your problem. Okay, so if you have any question you can ask me. I think it will be easy one. The main part is that where we have to find the compression ratio and how to find the cutoff ratio in this question. Okay, rest if we have all the values we can easily put in the efficiency equation. You can note it down, then I'll move towards the next slide. Yes, I have to solve another example, but now the time is limited, so we will solve in the next lecture. Okay, so this question you have to solve it by yourself. Okay, so it is a similar question which I already solved. So only thing is that here the values are different. So swept volume is given, clearance volume is given, maximum pressure is 50 bar in this case, fuel injection end at 7% of the stroke, the temperature start of the compression is given, so determine the cold air standard efficiency of the cycle. So it is a similar question, only the data is different. Okay, so if you have any question related to this you can also ask me. You have to note down the data first because you do not find out this problem in your textbook where it is from reference book, so you have to note down the data. So then I will stop the lecture. And all the students will get 0.2%, 0.2 absolute marks if anyone send it to me in a clear presentation.